Now, in the case of the AVL tree, remember that what we do is that we are going to insert as per normal, and then we are going to restructure the tree. Okay, so I'm just going to use some example first to get you some intuition of how it works. Let's assume that I'm going to just put in numbers based on the increasing sequence, right? Because that's easier to imagine. So let's say I start with 1, right? So 1 is going to have 2 sentinels, right? Now, at this point of time, this is balanced because the left side has a height of 0, the right side has a height of 0. So same height, no imbalance, right? Then I put in 2. So I put in 2, then I'm going to have 2 sentinels, right? Now, on the left side, I'm going to have a height of 0. On the right side, I'm going to have a height of 1. So the difference is only 1. So we can tolerate that. We still call that balance. Now, I put 3 in. Now, again, 2 sentinels, right? Now, at this point of time, the height of the right subtree is no longer 2. It's no longer 1. It's now 2, right? Because I have 1 and 2. So which means now there is an imbalance here because 0 and 2 is difference by 2. So this is no longer acceptable. So then we are going to have to restructure it. Now, where does the restructuring happen? Well, the restructuring is going to happen, right, starting from the point that is imbalanced. Now, the point that is imbalanced is this point. Okay, so let's call that Z. So that is a point that is imbalanced. We call that Z. And then we take the taller child of Z. The taller child of Z is the one that causes a problem, right? And though the taller child of Z, we're going to call it Y. And then we're going to take the taller child of Y. And we're going to call it X, right? Now, this taller child of Y, which is X, this is a culprit. This is the one that, this is a subtree that causes the imbalance to take place. Because we have added something there that increases the height of the tree to the extent that now it has violated the balance, and now I have to bring it back to normal, right? So that means we're going to call restructuring on this side. Now, how do we restructure on this side? Well, if we were to look at this case, it looks like this case, right? So basically, I have the following type of imbalance, which is I have Z, Y, and X, right? So then the only way, well, the way that I'm going to fix it is going to make B to be the new root and A and C to be on either side of it. So which means that if we were to think of this in the previous case, right? So then we're going to call this Z to be the A. We're going to call this Y to be the B. We're going to call this X to be the C, left to right. So this subtree is T1, this subtree is T2, T3, T4, right? So which means that after rebalancing, so what I'm going to get then is going to be 2, 1, 3. So we have rotated them, and so now it becomes 2, 1, 3. All right. So now it's balanced again. So that is the, now we're just going to keep doing this. And as you add more and more nodes, then at some point you're going to get an imbalance. And then you bring it back to balance by doing restructuring it. Okay, so initially when we talk about rotations, so I think the key idea of the rotation is that we would like to conduct a change to the structure of some subtree that is rooted at Y without changing the basic and ordering structure within the subtree itself. Now, I mean, throughout the slides here, I think what we try to do is that we try to capture the intuition of this. But I understand that some of you may actually want to look at the codes. So as part of the e-learn, right? So I think we put in the source files there as well. There is a source file there, and right now we are still in the implementation of the tree map, and the rotation is basically implemented as a few lines that basically tries to change the position of the A and the B. The A and the B is basically the X and the Y that we discussed there. Now, so this is a basic mechanism. And now the combination of rotations is going to give us the restructuring. Now, in particular, if you were to look at this restructuring, right? The first two, in fact, is a result of single rotation. So when we talk about rotation, we actually talk about rotating some child and a parent. So which means that in this case, what we're going to do is to rotate y and z. So the y is the child, and then the z, right? Now, the relationship between the y and the x here and the left on the right side, right, is the same. What is different is only the relationship between y and the z. So y and z are basically swapping their roles as parent and child. Now, in the example at the bottom here, again, so y and z, so they rotate. Now, as far as y and x are concerned, no change. So just y and z, right? And when you rotate it, y is now the parent of z. Now, in some cases, the restructuring is going to happen in the course of two rotations. So for example, in the case here, what we need to do is, if you look at what's happening on the right-hand side, right? Now, in the previous cases, the y's are the one that becomes a new root. In this case, the new root is actually x. So the new root here is x, right? And that's part of the reason why we do the ABC, is because we want to know what is the middle point. The middle point is going to be b. So in some cases, the b can be an x. In another case, the b can be the y, right? For example, in these two cases, the b are the y. X is the element that we want to promote all the way to the root of the subtree. Now, in this case, we need to do so through double rotation. So the first rotation is going to take x and y, they're going to swap. So x is now going to be the parent of y. And then in the second rotation, then x will now be the parent of y, right? So then x is going to rotate with z. So that x is now going to be the parent of z. So through the two rotations, we are promoting x to be the root, right? So that over its own grandparent, z. So the same way here in this case. So the first rotation, and then the second rotation. Okay, so now through two rotations, we're promoting up to the root. Now the b is going to be the middle point, which is going to be the root of the new subtree. Okay, now coming back to the notion of the AVL trees. So we are going to look at the sequence of operations that's going to keep it all balanced. Now, we are going to start from an initial state where we know that the tree is already balanced. All right, so we are starting from that initial state. Then we insert a new node. When we insert this new node, the tree becomes unbalanced. So clearly the culprit is this new thing that we are inserting, right? And now we're going to call that, let's say, P for now. So we insert P, and the tree becomes unbalanced. So that means that the part that will be unbalanced is going to be some ancestor of P, because P is the cause. So P is going to increase the height of all its ancestors by 1. So that means the parent is going to increase by 1, the grandparent is going to increase by 1, all the way to the top, right? Now, at some point, there's going to be some ancestor that has a left child that is not raised, but one child is not raised, the other child is raised by P, creating an imbalance. So let's call that ancestor Z, okay? So Z is going to be the earliest unbalanced node. So that means it's earliest, right? That means you start from P, and then you keep going up, walk up to the parent, to the grandparent, to the great-grandparent, encounter a specific node that is unbalanced. And the unbalanced node is the one with two children, left and right. And then they're going to have a height difference of more than 1. Okay, now that implies that Z has two children, right? So Z here is the earliest unbalanced node. Z has two children. Previously the height difference is 1, but now the height difference is 2. So it means that from 1 it becomes 2. Now, so we're gonna take Y and X, and Y is gonna be the taller child, and X is gonna be the taller grandchild. So which means that P itself is going to be the child, or P is going to be somewhere down the path of Y and X, because these Y and X are the raised path, right? The ones with the raised height. Now, so in that case, we would identify some Z, some Y, some X, right? So it's going to appear in that way. Then in that case, then we are going to do a restructuring on the X. on the restructuring on the X is going to push the Z down to contribute to the height of the shorter subtree, and then it's going to promote either X or Y up, and in the process, either keeping the height the same or shortening it a little bit so that to achieve the balance back. Okay, now let's take a look at some example, right? Now let's say this is the structure of the tree before insertion. This is before, right? So then we start from the top, okay? And we have two subtrees here, right? So T1 and the whole thing on the right here. Now, if let's say the existing structure is that this is H minus 1, this is H plus 1. So which means that on this side, this is H, on this side, this is H plus 1. So they are balanced, right? I mean, they are not the same, but they're only different by 1. So then we still call them balanced. Now, then we add something to the subtree at T3. So we add something there. And when we add something there, we're increasing the height of all its ancestors. So let's say P comes in here. So P increases the height of T3 from H minus 1 to H, which will in turn increase the height of X, which will increase the height of Y, which will increase the height of Z, right? So now at this point of time, we have H plus 2 here and H. Now they are different by 2. So right now we call it imbalanced. So in order for us to do this, we're going to restructure it with respect to these three nodes, right? X, Y, and Z. The middle one is the B, and the middle one here is X. So now X is going to be the new root, and then the rest are going to follow. Then if you look at the new configuration, then in this case, they come back into balance. So right now, the left and the right subtrees are of the same height again, right? So in that case, then they are now back to balance. So this is what the restructuring does, is that once it's in balance, because there is a heavier, not heavier, but it's taller on one side, shorter on the other side, then you're going to rotate it a little bit such that the original root is going to go down to the shorter side. And in that case, we are going to rebalance the height of the two. Now, this is another example. So here, this is a whole subtree, right? Before and after. And let's say you have just added the 54, right? Now, when you add 54 inside here, you create imbalance, right? Because this is a 3, this is a 1. So a height difference of 2. So now to bring it back to balance, you're going to rotate it. You're going to restructure it by rotating it to the other side. So now Z is going to come down. X is going to be promoted in place of Z. So as a result now, then the Z here is going to increase the height of this previously shorter one, because 78 is going to push 88 down, right? And then the two sides now are going to be of the same height. So they come back to balance. Okay? Now, deletion is the same, except that it's going to operate in the opposite fashion. So you're going to remove something, and suppose that the thing that you're going to remove is P. So again, you can go up and find the unbalanced node, right? The earliest unbalanced node. Again, it implies that Z has 2 children. So if Z has 2 children, then you pick the taller one. Now, whichever one is a taller child, it's not the ancestor of P, right? Because P is the one that's being removed. So the taller child is actually the other side. Then out of that taller subtree, again, you pick the taller child of that subtree. Now, in the case where they are of the same height, I mean, like Y has 2 children, the same height, then you're going to pick the one that is the same side as Y. So Y, if Y is a left child of Z, then X should be the left child of Y, okay? Now, then you restructure it on the X. Okay, so now let's take a look at an example. So in this case, we have the before and after. So here you have 44, 32. So we're going to remove 32, right? So this has been removed. Now, so then we have a height of 1 here. We have a height of 3 here. So that is now not balanced. So then the first one that is in balance is Z here. Where am I? Okay, Z here is in balance. So we're going to pick the taller child, right? We're going to pick the taller child. So the Y here, again, has 2 children. So we're going to pick the taller one. But they are the same height. So we're going to pick the one on the right, which is the same height, which is the same side to y with respect to y to z. So since y is the right child of z, so then we pick the x, which is the right child to y. Okay. So once we do that, then we have these three nodes, z, y, and x. We're going to do the restructuring. So then the z comes down. So the middle one, the b, which is now y, is going to be promoted up, and then the x goes up, right? Now, as a result, now it comes back to balance. Okay. So that is basically the process of the rebalancing. So once you understand the concept of rotation and restructuring, then the AVL tree is just a tree that is diligent at doing rebalancing. So it's going to keep inserting new nodes, and then at any point of time, it creates an imbalance, then it's going to pursue a rebalancing. Then every time you do that locally, right? And once you do it locally, as much as possible, you're going to keep the changes within that subtree. Okay. Now, in some cases, you may create a knock-on effect, because upon the restructuring of X, especially for deletion, what happens is that you could actually reduce the height of the subtree, which means that your ancestors may then get affected, because you're just one branch of them, of their subtrees, so it's going to create an imbalance on the other side. But if that is the case, then you just have to walk up and then just pursue the restructuring at each height of the time until the imbalance stops happening. All right. Now, previously we have an earlier claim, and the claim is that if you follow the balance property, then the height of the tree will be O log n, right? So there was the original motivation as to why we wanted to pursue this in the first place, which is to create an upper bound to the height of the tree that will still be in the order of O log n, right? So here we're going to try to justify that as to why is that the case. Okay, now so let's say you have an AVL tree, and you know ahead of time that the tree has n nodes. So what we are interested in is, can we find the worst case for the height of an AVL tree that has n nodes? So for binary search tree, the standard one, we know, right? So what is the worst case height? It's going to be ON, because you just have got the linear structure. So now for the AVL tree, we know that it's a balanced tree, because it satisfies the property that at any path, at any point, the two children of an internal node is only going to be differing by 1 in terms of the height. Okay, so we're going to make use of that particular property. Now, so let's say we are going to develop the base cases first. And what we're interested in is, we're interested in a minimum number of nodes of a height h, right? So we are saying that if I have a tree that has a height h, what will be its minimum number of nodes? What will be its minimum number of nodes? Okay, so if the height of the tree is 1, so then the minimum number of nodes to support a balanced tree with one node, one height of 1 is going to be 1, right? So for example, I have 1, and then this has a height of 1, and this is balanced, because the two subtrees on the left and the right is going to have the same height. So which means that then we can write n1 is equals to 1. Means that given that the height is 1, then the minimum number of nodes I need to support that tree is 1. So if the height is 2, then the minimum number of nodes that I need to support that tree is going to be 2, right? So in this case, this is the height of 2, right? So first and the second. And in this case, this is balanced, because on the left side, I have a height of 0. On the right side, I have a height of 1. It's still considered balanced. So which means that n2 is equals to 2, which means to support a height of 2, I need a minimum of 2 nodes. Okay, so those are the base cases, which is n1 equals to 1, n2 equals to 2. Okay. Okay, so then we are going to well, in some sense, you can think of it like an induction step, right? But we can establish the particular relationship between a tree of a particular height and its subtrees. So let's say I know ahead of time that I have a subtree and the height of the tree is h. So I know a particular subtree, the height of the tree is h, right? So which means that this particular subtree is going to have a root node of that subtree, and then it's going to have two subtrees, right? A left child and a right child. And I know because it's a balanced tree, so then at minimum, the height of one of them is going to be h minus 1. The height of the other one of them is going to be h minus 2. Because it's a subtree is of size h, right? So the root of that particular subtree is going to have two children. One can have a height of h minus 1. The other one can have a height of h minus 2. And this is the smallest one possible to still be balanced. Of course, you can say, okay, both of them is going to have h minus 1. Yeah, that's fine. Right? So that means that this is going to be bigger than the one that we have now. But we want to find a minimum. So at minimum, a tree of height h is going to have h minus 1 on one side, and it's going to have h minus 2 on the other side, to still keep this being a balanced subtree. Now, which means that if I'm trying to find out what is the minimum number of nodes that I can find within this subtree of height h, well, the minimum number of nodes here, which is the nh, right, is going to be whatever minimum I need of a tree of size of a height h minus 1 plus whatever minimum number of nodes that I need for a tree of size h minus 2. Then I need to plus 1 to account for the root itself. For the root itself, because the subtree is going to have a root and the two children, right, which in turn are the root of another two subtrees. So from there, right, this is the minimum. So which means that since this is the minimum, then I can rewrite this into an inequality. So it must be greater or equal, because any of these subtrees can actually be bigger. So for example, I don't have to have the minimum, I can have the maximum, right, of the subtrees of height h minus 1, or I can say that I'm going to have two subtrees of equal height. So both of them are going to be h minus 1. Now in either case, right, they're going to be more than this minimum. Okay. All right, now that takes us to this point. Okay, so that takes us to this point. Okay, so then now we're going to go on to the next part of it. Okay, so we can rewrite this, right? nh must be greater than 1 plus nh minus 1 plus nh minus 2. Now, the nh minus 1 is taller than the nh minus 2, because the height of h minus 1 is 1 more than h minus 2. So then the tree that is this tree is taller than this tree. If it is taller, that means that the minimum is going to be bigger here than here, right? So since I'm bounding this, then I can say that if that is the case, then I can use a smaller value, which is instead of nh minus 1, I'm going to use nh minus 2, which is a smaller value, and I'm going to still meet this inequality, right? Because I'm moving the lower bound lower. So which means that this inequality should still hold, right? And I can make the right-hand side even smaller by removing the 1. And the inequality will still hold, because I'm just lowering that further, right? I'm just lowering the right-hand side even further. So then at this point, then we can write that nh is going to be greater than 2 times of nh minus 2. Okay, so that's how we go from this one to this one. Okay, because the nh minus 1 is bigger than nh minus 2. So since I'm proving an upper bound here, right? So in that case, then I can lower the right-hand side, and I can stop the inequality I can still keep it to be true. I can remove the 1, it's still true, okay, because I'm just lowering the right-hand side. Okay, so now that takes me to this step, which is NH is greater than 2 times NH minus 2. All right, okay. Now let's take that step. Okay, so we are here now, and we see that NH must be greater than 2 of NH minus 2. Now, this particular equation, I can substitute the H with some other H, right? So suppose that instead of NH, I want to use NH minus 2. So in that case, then I can write this as 2 times, so H minus 2 minus 2. So this is going to be NH minus 4. So if NH is greater than 2 times of NH minus 2, and NH minus 2 is greater than 2 times NH minus 4, then I can replace this with this. So which means that now I'm going to have 2 times 2 of NH minus 4. Right? Now, NH minus 4 itself, I can feed it back into the same inequality one more time. So then instead of the 2 times NH minus 4, this particular part itself is going to be 2 times NH minus 6. So now I can keep going, right? I can keep going. Think of it as recursion. And at some point, I'm going to hit a base smallest possible case that I can get that is going to stop all this recursion from happening, right? So now you have 2 times 2 times 2 times 2, and as I increase the power of this, I'm going to increase the reduction on this side. Now, which means that I can more or less express this as 2 to the I times n times the minimum number of h minus 2i. So I is just some number. You can substitute it with some integer value, and this will still be true, okay? All right, so now what we want to do then is that we want to express this particular case. We kind of think of it like we are trying to roll out all the recursion until we get to the base case. So it means at some point, we have to get to the base case. Now, what is a base case? Well, this is going to keep getting smaller and smaller and smaller and smaller, but we know that it cannot get smaller than this or this, right? These are the smallest case. Objective now is that how can I get to that point? So which means that, all right, so how do I get to that point? Which means I need to figure out what is the value of I that's going to take me to one of these base cases. So it means that if my base case is 1, then I'm going to take h minus 2i, so h minus 2i, and I'm going to equate it to 1, because I want to get to the base case 1, right? So then if this is the case, then my I is going to be, well, in this case, it would be h minus 1 divided by 2, right? So that is going to be my I, right? Okay, now for this is for me to get to h minus 2i equals to 1. So this is one base case. Now another base case is h minus 2i is equals to 2. So that's another base case, right? Which in this case, then my I is going to be h over 2, all right? H over 2 minus 1, right? Okay, so that's basically what it is, right? Okay, all right. Now, this form, right? We can take either one of them because both of them are base cases. And if we take either one of them in the general form, we can write it in this way, where this is basically a ceiling function. It's a ceiling function. Okay, now for this particular I, we are going to end up with the two base cases. I'm going to get either one. But really, because I just need an I just need a lower bound, right? So which means that let me take the smaller one of the two, right? Because the smaller one of the two is going to be n1, right? Because I just need to get the smallest one possible. So then if that is the case, then I'm going to get this value. I'm going to replace the I with h over 2 minus 1, and then multiplied by the base cases, which is n1 or n2. In the case of n1, it's just 1, so that term is going to disappear. particular inequality. Now, if I rearrange stuff, right? If I take the log of them on either side of them, I take the log on the left-hand side, I take the log on the right-hand side. So the final inequality that I'm going to get is going to be this inequality, which means that the height h must be less than 2 log n. So the height h must be less than 2 log n. And this flows from the property that the tree was balanced in the first place. Okay, so for a balanced tree, the height is bounded by 2 log n plus 2. Okay, now what it means is that I can then write that h is O log n, right? That's just now flowing from the basic property of the big O itself. Not only that, since it is a binary search tree, I also know what is the smallest possible height of a binary search tree of n nodes. And that is going to be given log 2n plus 1, right? Which means that we kind of know now that not only is h is O log n, h is also omega log n. So it means that is lower bounded by log n, is upper bounded by log n, which means there is a tight bound. The height of a balanced tree will always be some order of log n. Now that then gives us the confidence that means that if we keep the tree balanced at any point of time, the height will always be in the order of log n. So meaning that any kind of searching and any kind of things that I'm going to do on this tree, as long as it is a balanced tree, we are guaranteeing that the complexity is going to be log n. Now, in the previous cases, what we see is that all of this is going to be OH, where h is the height. So then we can rewrite the complexity of the balanced search tree, which in this case is not just any tree map, but it's AVL tree map. It's a tree map that requires rebalancing. In that case, then, the complexity of this is going to be O log n. And this is a guarantee. So which means that no longer are we going to have the situation of a linear binary search tree. Because through this process, we are going to control the height of this binary search tree. Okay, so now this part of it, I think if you spend a little bit of time trying out this in a hands-on way, you're going to get much more familiar with the concepts that we are describing as part of this AVL tree. So what I'm going to suggest is that for the next 15 minutes or so, try it out by hand. Okay, so try this in-class exercise by yourself, right? Put it on a piece of paper, whatever it is, right? Try it out. Try to grow your AVL tree so that you get a hang of it, right? And then later on, we're going to discuss together as a class so that we can double check the answers. We'll do it slowly, step by step, so then you can see the progression and match it up to what you get. Now, the first thing I'm going to do is just to do the regular BST, right? Because I think the BST, by now, you should be quite familiar with this. So we get a for loop that basically goes from 1 to 10. And each time, we're going to insert the integer into the tree. And but in addition, when the integer is divisible by 3, then we are going to remove it from the tree. Okay? Remove sum I divided by 3. So that means at first we're going to start with 1. So 1 goes inside the 3. So 2 is going to follow on the right side of. Okay, so this is just a regular BST, right? Standard one. We are not talking about the rebalanced one. So then we come to 3. So 3 goes in, right? Now, but at this point of time, 3 is now divisible by 3. So then we will remove 3 divided by 3, which is 1. So which means that this thing gets cancelled out, right? Okay, so the next one is going to be 4, and then 5, and then 6. Now, when 6 comes, 6 is also divisible by 3. So we delete 6 divided by 2, by 3. So we delete 2. So then we get 7 and 8 and 9. Now, at this point of time, 9 is also divisible by 3. So we divide 9 by 3, which is 3. So we delete 3. Then we get 10, right? Now, at this point of time, we will exit the loop. So regular BST is going to create a structure to 3 in that sense. And within this sequence of numbers, the end result is still a linear tree. So then you still get something that is not balanced. Now, so what we hope is by using the AVL tree, then we are going to end up with a better shape of a binary search tree. All right, so let's do the AVL tree. Now, so the AVL tree, so it's still a binary search tree. So we're going to proceed initially the same way as we do it for a binary search tree. So we get 1, right? Now we insert 2, and then we insert 3. Now at the point of inserting 3, this is the first time when we create an imbalance. And the imbalance is going to appear right at the root, right? Because then this is the Z. On the left side, the height is 0. On the right side, the height is 2. So because we have 2 and 3, so then we need to restructure. And we're going to call restructuring on the taller child of Z, which is Y, the taller child of Y, which is X, right? And we have the ABC from the left to the right. So the B is going to be 2. So it's going to be the new root of this particular structure. So then we will have 2, 1, 3. So then at this point of time, after adding 3, then you're going to get this tree. But immediately after that, we are going to delete 3 by 3. 3 divided by 3 is 1. So we're going to delete 1. So then we're going to end up with this smaller tree now, right? So, okay, so let me see. This is basically add 1, 2, and 3. So we have the restructuring. And then we're gonna have the delete 1, right? So right now that's where we are. And then we're going to add 4. Okay, so when we add 4 to this, so all right, so we add 4 into the 3. So initially it's 2 and 3. So now we have 2, and then 3, and then 4. Another imbalance, right? So then we're going to fix it again. So then this would be this, right? We just need to rotate this. So now we come back to balance, right? So in this case, we have restructuring. And then we're going to add 5, right? So we add 5. So 5 is going to be the right side of 4. Now, in this case, the right subtree is a bit taller. But it's not so tall as to cause an imbalance because the right subtree is still height 2, the left one is height 1, right? So that means we're just going to leave it as by itself, right? As it is. We're going to add 6 to it. Now, when we add 6, so the previous shape is like this. So which means that 6 is going to go on the right side of 5. Now, at this point of time, there is an imbalance. And of course, there is an imbalance here, right? Because this is 1, this is 3. But the first imbalance actually happens at 4, right? Because at 4, the left is 0, the right side has 2. We conduct a restructuring, we're going to conduct restructuring rooted at 4, which means that this is Z, this is Y, this is X. So we're going to restructure it. So by rotating Y and Z. So then we're going to have 3, 2. Now this 4, 5, 6 is now going to be turned into 5, 4, and 6. So in this case, then this is going to be the result of the restructuring. And then after that, we are going to delete 2, right? Because right now we have 6. 6 divided by 3 is 2. So we're going to delete 2. So 2 doesn't have any child, so it's just going to go away. Now, when we delete 2, so that means 2 is going to go away. So we're going to have the following, right? 4 and 6. Now, deleting 2 creates another imbalance. Because right now, the 3 on the left side is 0. On the right side has a height of 2. So which means that this is now going to be the new Z. And then if we are going to restructure it, then the Y is going to be the taller child of Z. And then the X is going to be the taller child of Y. And if they are of the same height, it's going to be on the same side of y as y is to its parent. So since y is the right child of z, so then x, we're going to take this one. So then after restructuring, so what we're going to do is we're going to rotate this, right? So by the way, this is going to be the so-called T1, right? This is going to be so-called T2. This is going to be T3 and T4, which are all the subtrees. So which means that the new shape is going to have 5 as a root. And then we're going to have 3 on this side, right? 4, and then 6. So that is now going to be the result of the restructuring after deleting 2, right? So now we end up with this particular tree that is still balanced. Now then we're going to continue the process, right? We're going to add 7 to that. Okay, I'm going to continue below here. Okay, so maybe just let me continue here. Okay, so I'm going to add 7. So that is going to result in the following 3, right? 6 and then 7. So no imbalance, right? Because everything is still the same. I mean, not the same, but the height is still comparable. We're going to add 8 now. So 8 is going to create the following 3. Now, there is an imbalance. Now, not at the top, because at the top here, the height to the left is 2, the height to the right is 3. So 2 and 3 is a difference of 1, not a problem. The imbalance happens here. Because again, we have this where the left-hand side is 0, the right-hand side is 2, right? So then we have to restructure right there, where this is now going to be the z, y, and x, right? So upon the restructuring, so what we're going to have is that we have 5 here, 3 and 4. So 6 and 7, 8, right? So 7 is going to be the new one, and then this way, right? Okay, so this is the current shape of the tree. And what we're going to do now is we're going to add 9 to that. So, okay, we're going to add 9 to that. And that is 5, 3 and 4, 7, 6 and 8, and now 9, right? Now, at this point of time, we see that the heights are still balanced, right? Because we don't have any particular subtree that has a height difference of more than 1. So in this case, for example, this is 1, this is 2, right? It's children of 7. On this side, this is 2. On this side, this is 3, so still not a problem. But after adding 9, we need to delete 3. Right? We need to delete 3. So that means 3 is going to disappear. So when 3 disappears, so then 4 is going to take its place. And on the right-hand side, we have 7, 6, 8, 9. Now there is an imbalance, because here is 1 on this side, but 3 on the other side. So then we have to restructure again. Now the point of imbalance is here. So this is the z, this is the y, this is the x, right? So then if we do a restructuring, so in this case, then we're going to push the z down. 7 is going to be the new root. So 4, 6, 8, 9, right? So that is going to be the new restructured tree. And the final thing that we're going to do is to add 10 into. So we're going to add 10 into the tree. So we get 7, 5, 4, 6, 8, 9, 10, right? Now, is there any imbalance here? Yes. Where is that? The 8, 9, 10, right. So here it's z now, y, and then x, right? So we do a final restructuring. 7, 5, 4, 6, 9, 8, 10, right? Now, if we get the following structure of the tree, that if we were to compare it to what we would have gotten with a regular BST, we would have gotten this linear structure with a standard binary search tree. But through the sequence of the rebalancing, right, you get more or less a balanced search tree. So this creates basically a binary search tree that is going, and in the process, you're going to ensure that the height is going to be in the order of log n, and so as to ensure that you get the most efficient searches as possible. Okay, so the earliest imbalance is happening at 4, right? So in that case, so what is the question here? So that means the question is at what step to it? So the restructuring at this step, okay, let me just try to do this. So from here to here, right? So all the restructuring is confined to just this particular subtree, right? So that means that 5 is going to take the place of 4. So in that case, on this subtree, basically it's the same as this one, right? So I think that part is, is fine, right? Okay, so then we delete 2. So when we delete 2, so there is no more here. So this is z, this is y, this is x. So then we're going to call this a T1, which is subtree at T1. This is a subtree at T2. And the 6 here has 2 subtrees. It just happens to be empty, right? If we were to do in order traversal here, then we're going to have T1, Z, T2, Y, T3, X, T4, right? So this is going to be the in order traversal. And we want to restructure it such that the middle element is going to be the new root. So then the new one is going to have Y, and then Z on the left-hand side, X is on the right-hand side. This is T1, T2, this is T3, T4. So you just have to reconfigure this such that it comes back to this, right? Which means that for this, 5 is going to be the Y, right? This is the Z, this is the X, right? And this is the T1, and this is part of the T2. So that's how it gets to that part. So that is from the mechanism of the restructuring itself.
Prof.
Yeah.
Can I ask you for your number 4, right? How come you only have a T2 there and not another branching of, let's say, T2, T3?
Which one again?
The circled number 4 on the right. On the delete 2.
Yes.
Yeah. So
T3
this one
and T4 are here, right? It's actually below 6, below the X, right?
as in, I mean, for 6 there's 2 branches, right? Like 2 possible branches. Yeah. But then how come for 4 is only 1 possible branch?
Oh no. T2 is the whole thing. 4 plus its own 2 children. So basically, it's a whole subtree that has 4 and all its descendants. That is one we call T2. T2 is a whole subtree. It's not just a single node 4. It just so happens that here is a single node. So which means that in this case, the 4 actually has 2 branches to the sentinels, to the null pointers. But we are going to relocate all of them all as a subtree. So that means that the 2 children of 4 is still going to follow it here. So when we say T1, T2, and so on, these are whole subtrees. That means that we are illustrating this as being a part of a much bigger tree. We are trying to localize the changes so that we can encapsulate the whole descendants as a subtree. So the subtree is going to follow the parent. So in this particular case, the subtree is going to be whatever is to the left of Y. And that happens to be the subtree that has 4 in it. But it's not just 4, it's a whole subtree. So it has everything that has on the left of Y. Then Y is just going to transfer it to the right child of Z. So that it's going to still preserve the in-order traversal. Is that okay?
Yeah, I think that's okay, Prof. Thanks.